Hey Devin, I apologize for the slow response here. I started typing an email to you to respond to your questions from yesterday, and then decided maybe making a video would make more sense. I ran through it not fairly quickly at all. I was going to say fairly quickly, that's a lie. I ran through it very slowly, and it took nearly 20 minutes. So I'm going to go through this fairly quickly now. I think most of the questions could have been answered in the video today, but if not, maybe I'll cover them more specifically this time. First thing I'm going to say, and I think I mentioned it a couple times now in the various videos, you may or may not have seen them all. My feeling on math is it's not something to be memorized. And so these kind of rules that sometimes show up in a textbook or some other teachers kind of like, I don't always really worry too much about. My feeling is it's much more important for you to figure things out than to know things to start. It's kind of like a date in history. To me, that's pretty irrelevant because I can pull my phone out and find it within a couple minutes at most. But understanding why things happen, or the background and so on, that's much more valuable for sure. So I'm just kind of go through these fairly quickly, like I said, in order. So turning points. I think what you're asking there, and again, this would be one of those examples that I don't really worry too much about. But if you look at sort of the basic shapes, a first degree polynomial, which is a straight line, has no turning points. A second degree polynomial, which is your quadratic, has one turning point. Again, I'm assuming this is what you're talking about. I'm decreasing and then, oh, look, now I'm increasing. And if we follow that pattern, third degree, two turning points, it goes up, turns down here, turns back up here. Fourth degree polynomial, same thing, comes down, starts going back up, comes back down, goes back up. And so the number of directions that each graph covers looks like it's the same as the degree. So here we're going one direction all the way, which means 0 turns. Here we're going two directions, down, then back up, one turn. Third degree, we go up, then down, then up, two turns. The problem with that, and one of the reasons I don't use it, or I don't really like to use those ideas, is if we look at some examples, and this is going to be y equals x cubed. So here's the graph of y equals x cubed, and sort of the reason I don't like those turning point sort of rules is you can see here, if I've drawn it perfectly, which obviously I have not, the graph is increasing, goes through 0, and continues to increase. Here it's kind of opening up like in a downward fashion, sorry. Here it's opening upwards, but really there is no what I would consider turning point. So the rule really is first degree and second degree, the number of turning points is one less than the degree. But in these other ones, it's sort of the maximum number of turning points is one less. So a cubic can have two turning points, but in some cases it has, I don't know if you define that as 1 or 0. Down here, same thing. I've got the 1, 2, 3 turning points, the 1, 2, 3, 4 sections of graph, a decrease, an increase, a decrease, and an increase. But the regular graph, just the regular straight y equals x squared, actually looks like this. It passes through zeros, but it's like a flat-bottomed parabola. So it really just has that one turning point as well. Okay, so we didn't, seeing the turning points and understanding that there's a maximum number is valuable, but there isn't really maybe a good rule as to how many there should be. Now, I sort of looked ahead here and noticed that question 1 and question 5 I would give similar answers to. So I'm going to hit question 1 quickly and then go to question 5 because it's got a little bit more complicated a situation. So how can you determine the degree and sign of the leading coefficient? What you want to recognize is this can be expanded. And if it's expanded, you get y equals, and you get x times this times this times this, which will be x to the fourth. And then you get x times this and so on. And so there's going to be a series of values here. x to the fourth will be the first one, and then there'll be a certain number of x cubeds, a certain number of x squareds, a certain number of x's, and there'll be a constant on the end. That constant will come from the various values here being multiplied. So what's important is to recognize that, or sorry, I guess the one thing that's important that I didn't sort of see till I started to talk here is that the first term here, x, is actually x plus 0. And that becomes important only when I'm kind of trying to find this last spot. The last spot ends up being my y-intercept. And again, it's obtained by multiplying the numbers from each of the brackets. So 0 times -3 times 2 times 1, which means that basically it's going to be a plus 0. And so how can we determine the degree and the sign of the leading coefficient? Sorry, I guess I'm getting ahead of myself here. The sign of the leading coefficient is the value in front of here. It's going to be x times x times x times x. So it's going to be a positive value. In fact, it's going to be the number 1. The degree, again, will be obtained by multiplying x 4 times, so it will be x to the fourth. Now here's where the second part comes in. What's the relationship between the x-intercepts and the equation? Well, the x-intercepts are these numbers, or sorry, they're the opposites of these numbers. They're the values that when put in here will make each of those brackets go to 0. So when x is 0, I get 0 plus 0, or just plain old 0 times some other stuff. When x is positive 3, we get 3 minus 3 is 0 times some other stuff. And then when x is -2 and when x is -1, we will have other zeros there. So what is the relationship between x-intercepts and the equation? Well, again, it's the value that makes each term go to 0. And then the y-intercept is all of these values, and again, and this one here, which is kind of the real tricky key, combined. So the y-intercept is going to be, as we can see here, the value 0. So now what have I got? I've got a fourth power expression. It's got these 0 values. So my graph looks something like this. And again, continues out these two directions. So that leads us to number 5, which was basically sketch this graph. And I think you mentioned 5b specifically. So we'll look at it and determine, because there is a bit of a difference between it and the one we just did. So this, I guess we've kind of covered, right? Describe how a graph can be sketched using x-intercepts, y-intercept, and the sign, and so on. So we'll just look at this one. Forget about explaining it, but let's do it. My zeros are at positive 1, because 1 minus 1 gets me a 0. At -2, because -2 plus 2 gets me 0. And positive 4, so that's 1, 2, 3, and 4. Again, because 4 minus 4 would get me 0. The other thing to notice is the square on that first expression. So that means really what I have is x minus 1 times x minus 1. Sorry, x minus 1. And from what we saw, or hopefully what we saw in today's video at least, that means essentially there's a parabola right there. And so when I get to this point here, I'm either going to have kind of a bounce up here or a bounce back down here. Again, just a parabola shape in that exact spot right there. All other zeros we pass through. And so, so that's our x-intercepts. The sign of the leading coefficient will be of interest to us. And so if we did multiply this all out, we would get -2 times an x times another x times another x times another x. So our first term is going to be negative 2x to the fourth. The negative tells me my graph will be an m, not a w. And then the last thing is the y-intercept, we said, is obtained by multiplying all of these values together. But because there is a number out front here, it'll be multiplied by that as well. And so essentially my y-intercept, and I didn't really give myself enough space probably, will be the negative 2 out front times all of these values. So it's going to be negative 2, negative 2 times the negative 1. Wow. Oh my goodness. Sorry about this. I'm going to do it over in the corner here. So the y-intercept will be the negative 2 up front times the negative 1 from the first bracket. But because it's squared, there are two of those sets of brackets. So it's times another negative 1 times the positive 2 here times the negative 4 here. And so that's what? Positive 2, negative 4, positive 16. And so my graph comes all the way up here and hits at positive 16. So the graph is going to go this way. It's going to cross here. It's going to bounce back up here. And it's going to go back down through here. That's all the information I have. So part of your question, and the part of the question that certainly you can't know, is kind of how high does this go? Does it just cross right at 16, or does it actually go up here somewhere and come back down through 16? Or does it come up through 16 and then drop back down? I don't know that. And then same sort of thing here. How high does this go? Does it just kind of curl lightly? Does it just kind of little mound like this, or does it go way back up to some huge number? At this point, I don't know. I could plot a couple more extra points, but what we're doing is we're doing sketches based on what information we have. And the information we have is these are my x's, that's my y-intercept. It's a fourth power with a negative out front, so it's a flipped over fourth power expression. That means it's going to look like a letter M, and that's all I can do. In calculus, we worry about the actual maximums. We don't worry about them in functions at all. Unless, again, it's a key, maybe if it's a key point like a y-intercept, we'll find it almost by accident. But we don't go looking for those maximum and minimum values in this course. Okay, so hopefully that answers all your questions. The video probably ran longer than I wanted to again, but hopefully it's not a full 20 minutes this time.